In this video, I'll talk about how we extend the concept of simple linear regression to multiple linear regression so that we can model the relationship between a dependent variable y and two or more independent variables x's. We can apply simple linear regression model in the multiple regression model, which is often the case in the real world. We'll use Q to represent the number of independent variables in the regression model, so that this simple regression equation describes how the dependent variable y is related to the independent variables x1 to xq. And there is an intercept beta 0. Each independent variable has a slope or an coefficient that is beta 1 to beta q. And finally, an error term e. As in simple regression model, the error term in the multiple regression model accounts for the variability in y that cannot be explained by the linear effect of the q independent variables. In a multiple regression model, the error e is the mean of the dependent variable y when all of the independent variables x1 to xq are equal to 0. The interpretation of the y-intercept beta 0 in multiple regression is similar to the interpretation in the simple regression model. The slope coefficients beta j in the multiple regression model is different from the interpretation beta 1 in the simple regression model. In a multiple regression model, the slope coefficient beta j represents the change in the mean value of the dependent variable y that corresponds to a 1 unit increase in the independent variable xj, which holds the value of all other independent variables in the model constant. So in practice, the value of the population parameters beta 0 to beta j are not known, so we must estimate them from sample data. When we estimate, the beta values become b values. So this sample statistics provide this estimated multiple regression equation. As with simple linear regression, in multiple regression, we want to find a model that results in small errors over the sample data. We continue to use the least squares method, if you recall, from the simple linear regression model to develop the estimated multiple regression equation. So that is, we want to find the regression equation that minimizes the sum of squared residuals. That is the square deviation between the observed values of the dependent variable and the estimated or predicted value of the dependent variable. In other words, actual values of y subtract predicted values of y. The estimation process for multiple regression is shown in this figure. So the estimated value of dependent variable y are computed by substituting the values of the independent variables x1, x2, xq into the estimated multiple regression equation. So then the computer software package can be used to get the estimated regression equation and determine the regression coefficients b0, b1, b2, bq. So then we'll be focused on how to construct and interpret a regression model. Recall earlier in the trucking company's example, the managers want to estimate the total daily travel time for their drivers in order to develop better work schedules. So initially, the manager believed that the total daily travel time will be closely related to the number of miles traveled in making the daily deliveries. Based on a simple random sample of 10 driving assignments, we explored the simple linear regression model to describe the relationship between travel time y and the number of miles x. We found that the estimated simple linear regression equation for our sample data is y equal to 1.2739 plus 0.0678x. With a coefficient of determination, or r squared, the linear effect of number of miles traveled explains 66.41% of the variability in travel time in the sample data. And so 1 minus 66.41% equals to 33.59% of the variability in the sample travel times remain unexplained. This result suggests to the manager that maybe other factors can contribute to the travel times for driving assignments as well. So the managers might want to consider adding one or more independent variables to the model to explain some of the remaining variability in the dependent variables. So in other words, we want to optimize our linear regression model by introducing more axis or dependent variables that may lift the R-square or coefficient of determination. In considering other independent variables for the model, the managers felt that the number of deliveries made on a driving assignment also contributes to the total travel time. So then they added the number of deliveries for the 10 driving assignments in the original data, and they collected new observations over several weeks. So now the new data set consists of 300 observations, and each observation has not only the number of miles traveled, but also the number of deliveries made. So we now refer to the independent variables miles traveled as x1 and the number of the deliveries as x2. In multiple regression, R-square is often referred to as the multiple coefficient of determination. Our multiple linear regression with two independent variables would take the form of y equals to b0 plus b1 times x1 plus b2 times x2. And again, we can calculate the SSE, SST, SSR, and R-square using the same equations as explained earlier with the simple linear regression. I will make another video to demonstrate how to perform multiple regression in the Excel. But in the Excel output, as shown in the screenshot, the label for the independent variable x1 is miles, that is in cell A18, and the label for the independent variable x2 is deliveries, that is in the cell A19. The estimated regression equation is y equals to 0.1273 plus 0.0672 times x1 plus 0.6900 multiplied by x2. So how do we interpret this regression equation? That means for a fixed number of deliveries, we estimate that the mean travel time will increase by 0.0672 hours when the distance traveled increased by 1 mile. And for a fixed distance traveled, we estimate that the mean travel time will increase by 0.69 hours when the number of deliveries increased by 1 delivery. So our multiple coefficient of determination, or R-square, is equal to 0.8173. So we can compare to the results from the simple linear regression where we only use one independent variable, that is the number of the miles traveled, and our R-square actually improved. It improved from 0.66 to 0.81. So this means that adding the second independent variable, the number of deliveries, actually help improve the model. And as a result, it can explain more variabilities of the sample data. So with two independent variables x1 and x2, we now generate a predicted value of y for every combination of values of x1 and x2. So therefore, instead of a regression line, now we can create a regression plane in a three-dimensional space. Now, if you have more than 3 variables, it can get more complicated and you cannot visualize anymore. So this figure provides estimated regression plane for the trucking company example. It shows the 7th driving assignment over here in the data as the plane slopes upward to a larger value of the total travel time y. either the number of miles increase or the number of deliveries increases. As the plane slopes upward to larger values of total travel time y, either the number of miles traveled x1 increases or the number of deliveries increases. So this is the error between the predicted y and the actual y. The predicted delivery time and the actual delivery time. The difference is the error or residual. And that one's at observation 7 that has 3 deliveries and driven 75 miles. And the delivery time is between 6 and 8. So this observed value lies above the regression plane, indicating that the regression model underestimated the expected driving time for the 7th driving assignment. So they predicted lower than the actual value. Although we use regression estimators like B0, B1 from sample set to estimate the population parameters beta 0, beta 1, etc., we must recognize that samples do not replicate the populations exactly. Different samples taken from the same population would result in different values of the point estimators. So if the value of a point estimator changes relatively little from sample to sample, the point estimator has very low variability. So the value of the point estimators that we calculate based on a random sample will likely to be a reliable estimate of the population parameter. How confident can we be in the estimates? We can adjust such variability in potential values of estimators using statistical inference. Statistical inference is the process of making estimates or predictions and draw conclusions about one or more characteristics of a population. We do that through analyzing the sample data drawn from the population. So examples can be using a poll from a sample set to estimate or predicting voting results. To have a good regression model, we're looking for the error or residuals that's normally distributed, like in a bell curve, with a mean of 0 and a constant variance. And that the values of the errors are statistically independent. Let's visualize these two conditions. This figure illustrates the model conditions and their implications for a simple linear regression. So you can see that the mean error is 0 at each value of the x. However, regardless of the x value, the error term e and the independent variable y are normally distributed, each with the same variance. You can see the bell curve for each x value here. So the specific value of error e at any particular point depends on whether the actual value of y is greater or less than the predicted y. Simple scatter charts of the residuals and independent variables are very effective for assessing whether these conditions are violated. So we should review the scatter chart for patterns in the residuals. And ideally, we want to see the residuals consistently scatter around 0 throughout the predicted value of the independent variable. So this figure shows a random residual, so that's a very good model. Here, the residuals in the 4 panels show distinct patterns. Each of the patterns suggests a violation of at least one of the regression model conditions. So in panel A, a variation in the residuals E increases as the value of the independent X increases. You can see that the dots at the larger X are further away from the line of 0, suggesting that the residuals do not have a constant variance. In panel B, the residuals are more positive for the small and large values for the independent variable X, but are negative for moderate values of the independent variable. So it looks like a U shape in here. Because residual equals to actual value minus predicted value, this pattern suggests that the linear relationships in the regression model underpredicts the value of the independent variable, the value of dependent variable for small, a large value of the independent variable, and over-predicts the value of the dependent variable for intermediate values of the independent variable. The residuals in the panel C are not symmetrically distributed around 0. So many of the negative residuals are relatively close to 0, while the relative few positive residuals tend to be far away from the 0. So this skewness suggests that the residuals are not normally distributed. The residuals in panel D are plotted over time t. So this is time. So which generally serve as an independent variable, and that is an observation made at each of several and usually equally spaced points in time. So we can also see a kind of like seasonal or time-related pattern. So this will be means that it's underestimate because it's positive value of residual, and this means that overestimate because predicted is higher than the actual. So that's a negative value of residual. You can generate scatter charts of residuals against each independent variable in the model when using Excel's regression tool. You can select the residual plots option. So this figure shows the residual plots produced by Excel for the trucking company, where the independent variables are miles x1 and deliveries x2. So the residuals of which the independent variables are miles x1 and deliveries x2. So the residuals at each value of the miles appears to have a mean of 0. So they have similar variance and they're concentrated around 0. And then the residual at each value of the deliver also appear to have a mean of 0, right? So this mean of 0 is right in the middle of each one of them. The reason why this the dots looks like this is not because they have a pattern, it's because you have many number of deliveries ranging between 1 and 6, right? So there's no other values between 1 and 2, for example. So you don't have really number of deliveries of 1.5. So that's why you see a lot of the data. That's why you see the data points like this. But this doesn't mean that the residual has a pattern, right? So you just have this many observations that has 1 delivery, and this one has 2 deliveries, so on. And similarly, we have the number of miles ranging between 40 and 100. Each one group has a 5 miles difference. So it's like 40 or 45 miles, 50, 55 miles, and so on. There's no such as 44 miles or 42 miles in the record. That's why you see the data is displayed like this, distributed like this. It's not because they have a pattern, it's actually random, and the value can only be 40, 45, 50, 60, so on. So we can then use the Excel chart to create a scatter chart of the predicted value and the residuals similar to the chart in here. So the figure shows that the residuals at each predicted value of the independent variable appear to have a mean of 0. Right, so the dots all gather evenly above and below. So it means that these residuals have similar variance and to be concentrated around 0. So the residual provide little evidence that our regression model violates the condition necessary for reliable inference. We can trust the inferences that we may wish to perform on our regression model. So do we use the model as originally formulated with the non-significant independent variable, or do we rerun the regression without the non-significant independent variable and use the new results? So we say that if practical experience tells us that the non-significant independent variable has a relationship with the dependent variable, then it should be left in the model. On the other hand, if the model sufficiently explains the dependent variable without the non-significant independent variable, then we should consider rerun the regression without it. It is possible that the estimate of other regression coefficients and their p-values may change and when we remove the non-significant independent variable from the model. So recall that for the chugging company example, the p-value for the intercept B0 is 0.5354. So that suggests this estimate of beta 0 is not statistically significant. So should we move the y-intercept from this model because it's not statistically significant? So Excel actually provides us a function to remove the y-intercept from the model by selecting constant is 0 in the Excel regression tool. So this will force the y-intercept to go through the origin, and that is when the independent variables are equal to 0 and the estimate value of dependent variable would also be 0. However, doing this can substantially change the estimated slope in the regression model in a less effective regression that yields less accurate predictive values of the dependent variable. So since the primary purpose of the regression model is to explain or predict the value of the dependent variable for values of the independent variable that lies within the experimental region, so regression through the region origin should not be forced unless there's a strong reason for believing that dependent variable is equal to 0 when the values of all independent variables in the model is equal to 0. So in the trucking company's example, we only force the y-intercept to be 0 if we believe that if there's no miles traveled or no delivery made, there is no time spent. So most independent variables in a multiple regression problem are correlated with one another to some degree. For example, in the trucking company example, it involved two independent variables. X1 is the miles traveled and X2 is the number of deliveries. We could then compute the sample correlation coefficient to determine the extent to which these two variables are related. Doing so, we get the Rx1, x2 equal to 0.16. Therefore, we find some degrees of linear association between these two independent variables. So this is explainable because we know that the number of gallons of gasoline used usually depends to a large extent on the number of miles traveled. So in the multiple regression analysis, we call the correlation among the independent variables multicollinearity. We try to avoid multicollinearity usually. So according to a common rule of thumb test, multicollinearity is a potential problem if the absolute value of the sample correlation coefficient exceeds 0.7 for any two of the independent variables. So the primary consequence of multicollinearity is that it increases the variance and the standard errors of the regression estimates of beta 0, beta 1, beta q, and the predictive values of the dependent variable. And so inference based on these estimates is less precise than it should be. Next, you can check out the video where I create a multiple linear regression model in Excel.